In section 1 of FEA Done Series at Academy, we build the mindset. From now on, we build the engine. In this section, I'll give you a fast and easy overview of the finite element method, starting with the simplest element possible, a 2-node spring. Hi, I'm Dr. Iman. Welcome to section 2 of FEA Done Right Series at Academy. Some people refer to this theory as FEM, the finite element method, and distinguish it from FEA, the finite element analysis. The distinction is that FEM refers to the mathematical method, while FEA is the application of that method to solve real-world problems. But in practice, the two are tightly intertwined. Theory feeds analysis, and analysis informs better use of theory. So, in this video series, I use them interchangeably. For this review of the core steps in FEA, I refer to the foundational Academy video on FEA theory. Theory of finite element analysis, 8 simple and practical steps. You can find the link to this video in the description. I encourage you to watch this video in Academy to see the detailed description of all steps needed. The concepts in that video are based on one-dimensional models, which are great for building intuition. But to truly understand how FEA works in real-world applications, we need to move into 2D and eventually 3D world. And that's exactly what we will do in upcoming sections. Okay, let's dive into a quick review of FEA theory using a spring element. Let's start with a bigger picture first. Think about integrating a function from point A to point B. Instead of solving it analytically, one way to approximate the area under the curve is to break it into the small strips. Calculate its strips area and sum them all together. In finite element analysis, we apply a similar philosophy. Not exactly the same, but similar. Solving the full problem numerically all at once is often too difficult, if not impossible. So we divide it into smaller, manageable chunks called elements. Each element is defined by nodes, and we solve the problem locally within each element. Then, just like in numerical integration, we assemble the results in all the elements to approximate the behavior of the entire system. Another important point is that FEA lives at the intersection of mathematics and physics. You cannot rely on one without the other. Math provides the framework, the tools, and the language, while physics defines the problem, the governing equations, and the boundary conditions. Effective analysis demands fluency in both. Now, in the same video, we also walk through 8 key steps that are common to nearly every finite element analysis. I'll quickly revisit those here step by step as a refresher to get you ready for what's coming next. That is FEA in 2D. Alright, let's begin with the very first step in our FEA workflow. Selecting the element type and discretizing the geometry. If you're solving a one-dimensional problem, you can use a simple element that connects 2 nodes, as shown here, with nodes I and J. Now, along with choosing the element type, you must also consider the field variable, the unknown you're solving for. This is represented by the degree of freedom, or DOF, at each node. For example, in the case of a structural analysis, the field variable is usually displacement. So at node I, you have a displacement value ui, and it is uj at node j. These degrees of freedom are what the solver ultimately computes, and everything else like strains and stresses gets derived from them. Once your element type is chosen, you move to discretization, which simply means dividing your geometry into elements. This is equivalent to numerical integration when we divide the area under the curve into smaller pieces. For the spring structures and also trusses, discretization is already carried out, as each spring or bar is an element. But for a general 2D or 3D geometry, an actual discretization must be done. This is called meshing. Okay, let's go to step 2. After we have selected our element type and discretized the model, the next step is to define how the solution behaves within each element. And that's where shape functions come into play. Shape functions are essentially our best mathematical guess for how the field variable, like displacement, varies inside an element. For simple one-dimensional problems, a good place to start is with a linear approximation. Let's look at this example. We have a spring of length L fixed at one end and subjected to a force F at the other end. We want to estimate how displacement U varies along the length of this spring. We start by proposing a simple and reasonable guess. U is equal to A1 plus A2x. This is a straight line function. It's easy to work with and satisfy the requirement of being continuous across the element. Now, to express this in FEA terms, we rewrite it in matrix form. Yes, everything in FEA is written in matrix form. U equal to NA. Here, N is the vector of shape functions, and A is the vector of nodal displacements. Those are unknowns we want to solve for. To me, this formula is the foundational building block, the central pillar of the FEA. For a two-node linear element, using the boundary conditions to find A1 and A2, the shape functions become N1 equal to 1 minus x over L and N2 is equal to x over L. Now, I know I'm moving fast and skipping some middle steps, because this part is just a review. If you want the full detailed walkthrough, please watch the original Academy video I referenced earlier. Let's go to step 3. Once we have selected our element and defined the shape functions, the next biggest step in FEA is to derive the element stiffness matrix. This matrix is at the heart of the finite element method. It connects the nodal displacement to the nodal forces through the relation F is equal to K element A. This is what we call the element characteristic formula. This 2x2 matrix is the element stiffness matrix KE. It tells us how much force is required to produce a unit displacement at each node, assuming all other nodes are fixed. This matrix is always a square, and its size is equal to the total number of degrees of freedom for the element. For example, here, for a two-node spring element with 1 degree of freedom per node, the size of the element stiffness matrix is 2x2, as we have a total 2 degrees of freedom, Ui and Uj. And before I forget it, I need to mention that this step is like finding the area of each strip in numerical integration. Let's go to step 4. So far, we have derived the element stiffness matrix. Let's move one step forward and build the total stiffness matrix for the entire system. For this step, we need more than one spring. Let's just make a system with 2. And again, to use the numerical integration analogy, this step is equivalent to adding the areas of all the strips under the curve for numerical integration. Okay, we have 2 elements now. Element 1 connecting nodes 1 and 3 with a spring stiffness K1, and element 2 connecting nodes 3 and 2 with a spring stiffness K2. Each element has its own stiffness matrix. Both are 2x2 because each spring has 2 nodes and 1 degree of freedom per node. Here I need to mention this. I say each spring has its own stiffness. But remember, that's based on physics. In physics, we say this spring has a stiffness K1. But in FEA, we have a little bit different perspective. Instead of having one single number for a spring stiffness, we have a matrix, because now we are talking in FEA. As I mentioned before, the element stiffness matrix is 2x2 because each spring has 2 nodes and 1 degree of freedom per node. Now, for element 1, the stiffness matrix is K1, negative K1, negative K1, K1. And for element 2, the stiffness matrix is K2, negative K2, negative K2, K2. To build the total stiffness matrix, we need to assemble these element stiffness matrices into a single matrix that accounts for all the degrees of freedom in the model. This is called the assembly process. This process is not just simply done by adding the 2x2 stiffness matrices, because that would result in another 2x2 matrix. Here, physics helps us show why the total stiffness matrix is a 3x3 matrix shown here. Just a quick note here. For this system, we have total 3 nodes. Therefore, total 3 degrees of freedom. So the size of the total stiffness matrix has to be 3 by 3. This matrix fully characterizes the stiffness behavior of the entire spring system and relates displacements to forces through the equation that we write in the next step. Now that we have found the total stiffness matrix, we can go ahead and write what's called the characteristic formula for the entire system. This is the fundamental equation in finite element analysis that relates the total external forces shown as vector F to the nodal displacement shown as vector A. Here you see how this looks for the entire spring system. We have the total stiffness matrix on the right multiplied by the displacement vector, and the result gives you the global force vector. This equation captures the mechanical equilibrium of the system. But here is a problem, and it's a very important one. This system cannot be solved yet. The reason is mathematical. The total stiffness matrix is singular, meaning that its determinant is 0. In other words, it doesn't have an inverse. What does this physically mean? It means that this system of 3 equations has infinite solutions. Because under force and in the absence of constraints, the whole system can move in the force direction. Another name for this is rigid body motion. So each node has an infinite number of values for their degrees of freedom. See, again, physics. So although we've assembled the system correctly and written the proper characteristic equation, we cannot move forward until we restrain the rigid body motion. We do this through constraints. In the next step, we'll see how applying those constraints make the system solvable and physically meaningful. Okay, in step 6, let's apply constraints and external loads, known as boundary conditions. This is where the model becomes grounded in physical reality. Let's start with the constraints. In this example, node 1 is fixed. That means its displacement u1 is 0. This constraint removes the possibility of rigid body motion. In other words, we're anchoring the structure so it cannot float freely in space. What happens mathematically? When we apply this displacement boundary condition, the original total stiffness matrix, K total, which was singular and unsolvable, transforms into a new matrix with a non-zero determinant. We also update the force vector to reflect the known external load. In this case, a force F2 is applied at node 2 while all other nodal forces are set to 0. This gives us a new system of algebraic equations shown in matrix form as F K total with superscript BC times A. Visually, you can see on this slide how the constraint modified the total stiffness matrix. The diagonal element turns into 1 and the other elements in row 1 and column 1 are changed into 0. With this update, the system is ready to be solved for the unknown nodal displacement because now the new total stiffness matrix is invertible. Again, note that I'm only showing you the final results of the application of the constraints. The detailed description of this procedure is available in the Macademy video I have mentioned before. Before I leave this slide, I also want to draw your attention to a very important technical point. At node 1, we wrote the force as 0, but in reality, the actual force at that node is not 0. When you apply a constraint in FEA, the system generates a reaction force at that location. This reaction is equal and opposite to the external applied force at node 2. However, we set it to 0 in the vector not because there is no force there, but because reaction forces are not considered external loads in FEA. If you turn this into a system of algebraic equations, the first equation is u1 equal to 0. That is our constraint. See, the reaction at node 1 doesn't even enter the equations. Let's go ahead and solve this equation in the next step. Now that the constraints have been applied and our system is no longer singular, we've arrived at the solvable version of the finite element model. F is equal to K total with BC superscript times A. And the goal is straightforward. Solve for the unknowns, which are the field variables, the nodal displacement in this case. Since K total with superscript BC is a square and invertible matrix thanks to the constraints, we can now find A vector by multiplying both sides by the inverse of the stiffness matrix. And this gives us a unique answer, not like before application of the constraints that we had infinite solutions. Now let's go to the final step. We have solved for the nodal displacements, and now comes the fun part, post-processing. This is where the physical meaning of FEA results come to life. From the nodal displacements, we can compute a strain, stresses, reaction forces, and even quantities like contact pressure and a strain energy. Let's go through a basic example to show how this works. We already have the displacement field interpolated as u equal to 1 minus x over L times u1, u2. Now, to find the strain epsilon x, we take the derivative of displacement with respect to position. Epsilon x is equal to du over dx. Here you can see the derivative of the shape function with respect to x. Negative 1 over L times u1, u2. And if this matrix form is converted to an equation, we have negative u1 over L plus u2 over L, or u2 minus u1 over L, which is delta over L. So clean and elegant. This is the axial strain in our one-dimensional spring element. From there, computing the stress is simple using Hooke's law. Sigma x is equal to E epsilon x. But remember, the work isn't done yet. The results we just computed must still be verified and validated to ensure they are both numerically accurate and physically meaningful. We'll discuss that crucial step later in the future sections of this video series. Now that we have revisited the basics of the theory of FEA for 1D spring element, it's time to widen the lens. Finite element analysis offers a whole family of elements, each tailored to different physics and geometries. In the next section of FEA Done Right series, we introduce the most common and practical elements in finite element analysis. See you soon.